Now we're going to look at liquids. Your particles inside a liquid are in constant motion. The particles, they can vibrate and they can also slide past one another. And since they can slide past one another, we can say that they're fluid. Your liquids are about 1,000 times more dense than a gas. So the density of a solid and a liquid, they're very, very similar compared to that of a gas. Gases have a lot more empty space inside of them than solids and liquids do. Because the particles are so much closer together, the intermolecular forces are a lot stronger because they're dependent on distance. This is why there's a greater attraction to other particles in a liquid than there would be in a gas. Because they have a greater amount of attractive forces, your liquids are more ordered. And because they're more ordered, they have less entropy, because entropy is a measure of randomness. So you have a lot of entropy, you've got a lot of randomness. Some properties of liquids that I'm pretty sure most of you are already aware of are that liquids have a definite volume. So they're not going to expand or contract like a gas would. You can't really easily compress them and smush them down into a smaller space because they don't have as much empty space in them as a gas does. Since the particles can slide past one another, they are a fluid, they can flow. Because they have this ability to slide past one another, they have an indefinite shape. Liquids can also diffuse into one another. So if you put a drop of dye into water, what happens over time is that the dye molecules spread out throughout all of the solution until it's evenly dispersed. Liquids also have something called surface tension, and what surface tension is it's a force that pulls your neighboring parts of a liquid at the surface together. So if I have a molecule that's up at the surface, I have stronger attractive forces to the neighboring molecules than it does to the gas that's up at the top, above the solution. So because these are all attracted to one another and not attracted to the gas that's up here, I get something known as surface tension. Okay? Now, what that does is these guys want to be together as much as possible. So what you'll see in nature is that you have a lot of curved surfaces. So like a water droplet on a leaf, or if you drop something in the water, you'll see a drop come up that's a sphere, or like a teardrop shape. Because of gravity, it kind of elongates it out. Well, why does this happen? Well, you can have the largest amount of volume with the smallest surface area in a spherical shape. So by nature, because we have the surface tension, a lot of things pull into a spherical shape, or a sphere-like shape, like a teardrop, where it's an elongated sphere due to gravity's pull. Capillary action is the attractive force between the surface of a liquid and the surface of a solid. So if you stick a really narrow, thin tube into something like water, what happens is the water is attracted to the side of the glass, and the water will actually rise up through the narrow tools because the attractive forces are pulling upward against the force of gravity that's pulling the water down. The water will actually climb up your capillary tube until the weight of the water is equal to the gravitational pull that's pulling it down. This is the reason why we see a meniscus. So if I'm looking at something like water, which is polar, of course I'm going to read at the bottom of the meniscus to read my volume. The reason why we have this pull upwards is that my molecules are attracted to the glass. Why? Because water is polar, and so is the glass. So I have this dipole-dipole attractive forces because between the glass and the water molecules. And this attractive force is strong. If I look at something like mercury, if you look at Mercury, the meniscus actually curves downward. And the reason why I have this downward curve is because there's very little attractive force between my Mercury atoms and the glass. There's a lot more attractive force between the Mercury atoms themselves. So that's why I have this downward curve where all of the Mercury atoms are trying to stay together as much as they possibly can, and I get something that looks a lot more like surface tension.